So, hello everyone. Today we're going to start discussing a bit about the coursework. So, if I haven't already made that clear, so let me clarify something regarding the coursework. So, as explained from the first lecture, then when you're using, so the first part of the marking screen is actually unrelated to any use of concurrency. And it's just related to the program correctness itself. So I'm aware that now you don't have all the constructs that are required for concurrency, but you have, as I was mentioning in the first lecture, automated tests in order to check whether the implementation is still correct, even though you are considering the main thread as usual. So the thing that I would suggest, if you have feeling pressure due to the other team project, is to start doing the coursework and fill in the methods while checking for the correctness of your assumption. Because then, if your program is not correct, and then, in addition to that, is not concurrency correct, then it's going to be very much a mess. So it's actually better to start gradually and first check the correctness of the program independently from the usage of multi-threading, and then later on to check whether by adding threads then you're achieving the expected solution. So, and as I was saying, then some of you during the coursework didn't find where the code base is, so either you're going to GitHub or you're accessing Canvas and then you're downloading the zip. After you unpack the zip, you're just opening that folder, you would have automatically a Maven project. So as provided in the specifications, please do not change the classes in any way, so in as much as different package structure or anything, because we're going to run automated tests. Otherwise, that will make the hard for us marking your 100 and more scripts. And having like a uniform API also to ensure a fair evaluation for everyone, so we know that basically in order to look for something, we're going to look at that method, so we're not going to look at 100 different possible implementations. Okay, so besides that, do you have any questions related to anything that was taught beforehand? No questions? So the thing is, by the end of the week the last frontal lecture related to the just to the material, then I'm going to release basically what's called a survey on which you could say which argument was not clear. So even though you are not explicitly raising your voice and telling that to me, it's just going to be a pool. From that, then we're going to see which are the topics that are less clear to you, and then in the remaining part of the module, so in the remaining 2 weeks or so, we're going just to repeat the topics that were less clear to you, and in addition to that, we're also going to see the exercises. So that is just as an organizational note. So let's talk about a bit the coursework, shall we? So what that is going to be about, a blogging platform. So I know that is an old concept, but now you could think about that like if you're using Reddit or something, it's going to be similar. So in here is actually something that I was looking at. Okay, so even you might have a blogging platform on where you could ask for advice to someone, for example. So I have a problem, and then, or Yahoo Answers if you want to do that in another way, or Quora or anything. So I want to implement a server for a blogging platform where we have multiple users that can also be moderators. That is actually just an oversimplification. Just to say that someone could also really remove completely a topic. So under this assumption, then the thing that we have we could think that each user is mimicked by your program as an external thread, or a thread which is actually running in your PC. Why? Because even that is going to mimic realistically what happens in a server, where you have multiple connections going to access the platform itself. And then you'd have, for sure, concurrency issues. Why? Because you might have someone trying to write something, and then you have two users trying to do a post at the same time, or to create a new topic, or anything of the sort. So we are also assuming, as I was said, that also all the users are also moderators, and they can also delete entire threads. So in here with thread, I mean topic thread. Okay, so they could eliminate a topic thread. Furthermore, the users can also list all the existing threads by name, as well as list the messages within the same thread topic. So in here, everything is provided in a verbose way, but then in the code, you already have the methods doing so. So you have one method for actually retrieving from the blogging platform instance directly the topic name, or posting the message. So everything is already provided as a set of methods. Consider transactions as sophisticated type of atomic operations. Why I'm saying this? Because then you could consider that you have a transaction that is going to be run, and this transaction is the thing that we were calling beforehand like a thread. So a transaction could be seen as a set of operations up until you have like commit or like an abort operation. So you could think that it's just something atomic whenever you're invoking a method. So for example, clicking the send button, or retrieving all the messages because you want to display something on your browser, then that is just an atomic operation. So either it's performed or not. And those are what are going to be. That is actually just an intuition what is a transaction, but it's just a reflection of what we were seeing beforehand last time. You could think about a transaction as being a logical unit of processing within an executing program, including one or more atomic operations that should be interpreted as an atomic sequence of operations. So in here, and so to speak, I will also, one of you also provided, started to do the exercise for exam 4. One of the problem was that they were updating directly the global copy of a variable, and they were not assuming that you have an abort operation for which you should fall back to the previous value. So they were still aborting the computation and not restoring the value as it was before. So an abort operation should roll back entirely any kind of change, while the commit validates the change that you have. So that is actually important. Anyway, you have the solution for all the exercises. In there should be also some comments. If the transaction terminates successfully, then we can inform the system that it completed, and any kind of transaction could terminate due to a system failure, unhandled exceptions, killed operations. This can be mimicked by an abort operation. So that is actually what we're doing. Also, in the exam and the exercises, we're not going to specify exactly what is going to happen. We know that something bad happens, and so we want to undo all the changes. And that is actually what is doing. That is actually also important to some extent, because it gives the notion that you're not just working on your specific program, but you're thinking that you're sharing something with someone else. So you're just providing the result once you're sure of what you're doing. So that is actually a best practice, to just update your local copy, and then when you're sure of what you're doing, you're committing, and then you're publishing the result. So that is actually what the commit is about. And abort is just undo any kind of operation that was pointless. So in here, I'm just providing all the set of information, but it depends really on how you want to implement your operations. In here, we're just considering atomic operations or very pointwise operations as you would do in a graphical user interface. So you're just clicking on the button and you're doing something, you're posting a message, and then you are just sending the message through. But for example, a bank transaction could be more complicated than that, because you could also withdraw some cash, you could do a loan, you could do multiple things, and then you could decide, okay, no, I do not want to do that. Or for example, even if you're paying in Amazon, then there is actually an error while transferring and doing the payments. You're accessing, for example, your app from a mobile phone for confirming the purchase, but then you are repenting yourself to say, okay, I want to undo that. Somehow you cannot undo. You are detaching the Wi-Fi from your mobile phone, so to not give you the permission of doing the operation. So you're doing multiple things with your app, and you want to undo that entirely. So that's why sometimes, if you are doing a lot of operations, you might be required to log whatever a user is doing, so to actually undo the set of operations. Or another use case example, I'm aware that most of you are not using Linux, because I see a lot of Macs in here and Windows computers. Anyway, if you're using a Linux operative system, the file system is quite different. To some extent, maybe a Mac OS could also have something similar. But if you're using like ext4, then you also have a logging system. So something might go wrong. You could close your computer. You could shut entirely while you're writing a file. Still, the thing that would happen is that before making the operations effective, the thing that you're doing is taking a journal of what the process is doing, and only when confirmed, then you are actually applying the information and the changes to the file system. So that's why you have some file systems that have journals. So whenever something goes back, you could also have like half of the information that you were writing in the log. And that is also something that might be done. And the log is also important in order to undo some set of operations, or in a very safe protocol, you're just logging the operations, and only when confirmed, you're just writing the information back. So that is really dependent on what you want to do. So, and that is basically what I was saying. In here, I just provided further information from the El Masri Navate book, on which basically they're providing some hints of what are transactions, but those are just for if you want to deepen the subject. But they should not be related to this coursework. They are more related to the first coursework that you also have in the code base and on GitHub and the specifications. But for this simplistic scenario, it should not be required to do so. So if you're also going into that coursework, then the thing was more simplistic. So you just had read and write operation like withdraw and put money in the bank account, then closing the bank account, or not even that. So it was just putting money and taking money, and then committing the operation or aborting the operation. So, and then that required to actually have a log, but in this scenario, it should not be required. You would also use atomic operations. Then, for sure, in the marking scheme, you have the possibility of gaining more points if you're doing beyond what is required. So if you're trying to mimic as much as possible as a realistic system, where you're also trying to mimic like handling requests from a server. But that is actually not required in here. Then the first line is actually the thing that I was saying in here. We're trying to mimic an industrial setting, not if you're going to work in a very small startup, but definitely if you're going to go for a big company on which you're starting to work in a project. You have a project manager that creates the UML diagram and then creates like is actually a system person, so is designing the entire architecture, and then is actually saying, okay, your task is actually to implement the methods from this class. And so you're not there to say, okay, I want to change the API, because actually otherwise you will make the life miserable for everyone else. If they already give discussions, they already agreed on to do something, and then suddenly you decide to do something different, and then the entire project not compiles. Or, for example, you're, okay, but I will change the semantics of a function, that nothing else will work because you have a documentation and you didn't abide by the documentation. So in here is actually extremely important that you keep the same API of the project, and you try to keep the same package structure, and to do what the method tells you. As you would see in some parts where the information that you pass to the parameter is not so clear, I try to add comments, so to say what should be the parameter, what should be the effect of the method that you need to implement, and what should be the result. So you'd have like a proper industrial setting, not like an academic setting where you just write the code and then you have it. So in here, you're not required, even though we are doing like a blogging platform, you're not required to create an HTTP server. You're not required to use handling TCP connections from an HTTP protocol, nothing of that. Just create some simple threads and then run and simulate each thread as being a user interacting with a blog platform will do. So, because the entire HTTP server is going to be mimicked by a monitor, and hopefully by the end of Friday you would see what a monitor is, which is just handling the requests. So it's just going to be a mediator of all the requests. It's going to be a class basically shared across the threads, and that is what the blog server will be, just a monitor where you have a lot of variables. That is another simplification, but it's just good to do something with scale, so starting with something simple, and then you know how to implement actually a proper server. And very importantly, you need to ensure that you have no race conditions, so no of the issues that we've seen in the first lecture. No read-write, write-read, or write-write conflict, as we've seen before. So in here, you're not even required to tolerate the virtual crash of the computer, of the server, but that might be like something additional. So let's suppose that the blogging platform itself goes down, then you're putting up the server, and then you're losing all the information. So usually you have like a backup measure, like you're storing the information into like a database, and then when the server is going to be up, then you are retrieving the same information. So this is actually a precautionary measure which is not required. So I'm just saying here what is not required. It's just saying you're not required to do this kind of complexity, but I'm just showing you what kind of complexity might be required in the real world. When in the real world you have more than 3 weeks to do something. So that is just addressing the actual complexity that you are going to face after you decide to pursue your non-academic job. Or still, even if you're working like in creating like a user interface, you might also encounter this kind of problems. But we have a very lower risk of getting fired. Be aware the given code base provides a simplistic solution which is not correct for the following reasons. So it's not even correct, it's just that the API is looking good. So that in that extent is correct. In the previous version, when the coursework was more difficult, I actually provided a correct, so that was last year, a correct solution, but still it was not using multi-threadedness. And the issue was how do we ingest the multi-threaded part. In here, I did like a different kind of choice. I provided all the tests for the non-multi-threaded part, and then given the tests, you should be able to implement the missing methods. So in here, you could have this kind of problems. But that is actually mainly related to previous years. So in here, just to clarify, and I will rectify the slide, with due time, you don't have actually the implementation which is actually correct. If you're taking all the methods, they're doing nothing at all. If you're taking the code base, you have just a bunch of to-dos. So I need to amend the content, really. But anyway, as I always say, the key of success is actually asking. If you are just self-assured and then you're saying, okay, I think I understood, but you're not sure, then you're going to have what you're having, which might be correct, which might not be correct, but then you didn't have the opportunity to ask me, and that's why you're having like the courseworks, to ask questions, not to make us walk around and do nothing. So I'm expecting that eventually the coursework room will be very busy and all the demonstrators will be replying to your questions. So before starting like drafting of the documentation of Java, do you have any questions regarding to the coursework or anything that was discussed beforehand? Yes.
In the coursework, we have a lot of fields, such as project 1, project 2, and project 3. Do I need to
just project 3?
Do I need to delete one?
You're not required. So you need to just keep project 3. Let me clarify on that for everyone. So let me show what is actually referring to. Okay, so if I go to, I don't have that in here. So, good question. So if you're going to the code base, you actually have project 3, and that is already the code that you should be extending, okay? So the task of a project is not rewriting these classes, is actually to extend the classes in terms of adding the code. Let me clarify again. If you go to events and then you go to testing 3, you have all the tests that the first half, for sure, of a test for the correctness of a program. So you see test 1, test 2, test 3. And those are assuming that you have the class structure as in the block class. So please keep these classes and please keep the entirety of project 3. So as far as I'm concerned, you could keep all the packages that you have inside and just add the methods. For example, in here, if I'm just running this, you'd see that some tests are passing and some are not. You see here, some of these are green, it means the test passed good. Some of those in red, it means the test not good. And then you have actually the student ID, which is in here is just 1, 2, 3, 4, 5, 6. So let's suppose that you have like multiple errors, the thing that you're going to have, and then in the terminal you cannot see everything. Then everything is going to be written into an HTML file, which is going to look similar to nothing, I assume. Yeah, because now it's completely blank. But anyway, yeah, because that was not fully attached. So let's close. So FOS, here, stability, 1, 2, 3, 4, 5, 6. So allegedly, you should also have a way to write the file. Seems not to work now, but anyway, for the moment, if you're not using like multi-threaded program, then you're not going to have like multiple tests that are going to exceed the maximum space of the console. Therefore, at this stage, you have all the output on the terminal. Anyhow, the thing that I'm also trying to do, and I will try to amend that, but there's going to be just a test fix on the testing class, is to have like the results on the HTML file, so you have a better view of that. And the other thing that you have is actually a tentative amount of the score, so you have basically what your final score is going to be. So now, if you're just running the code as it stands, you're having a score of 11 out of 90, where the other 10 extra points are going to be the extra marks. So if you're just using the code as it stands, you're starting from 11 points. And given that the marking scheme is going to be one-to-one mapping to this, then you should expect that at least for the 50 marks, you're going to receive the exact same score. So given that, and let me show also the thing that I was referring to before, if you're going to the blog class, then you'd see in here a lot of to-do, implement this, to-do, implement that. If you go to the, what was it? If you go to the latest operation set, you have to-do, implement this, and then you have like some kind of guidance in here of what the method behavior should be. So please do not remove these classes because those are there to help you in the implementation and to disambiguate whether the PDF is ambiguous. Does that answer the question? Good. Any other question? Yes?
So, concurrency, when we are dealing with an application involving a database, do we handle concurrency mostly at the application level, as in the database operations are always sequential?
Thanks for asking that. So let me respond to that question in two ways. One, if you're using a relational database, then you're cheating because you're demanding the relational database to handle all the concurrency. So please do not use any kind of relational database because that is already handling the concurrency operations for you. So the task of the coursework is actually implementing that on Java. Otherwise, you have at all no use of locks, no use of semaphores or what have you, and you're just demanding everything to another application which is dealing with concurrency for you. So that is actually the short question, what might be a follow-up, but the thing that I want to word before it. The second part of the question is actually the thing that you were asking, which is how does a relational database operate, actually, which was your real question. The real question is going to be that it depends on the query that you're providing. Basically, at the configuration, you could also set up, which is the protocol. It depends on the relational database. But you could set which is the kind of protocol that you want to use. Not necessarily you're using a strict-to-face locking, because that is too strict. But they're going to use more relaxed versions. So usually, they're going to do like an optimistic protocol on which you're trying to do something. If something goes bad, you're logging all the operations, and only the thing that was confirmed then is going to be applied. So they have a lot of journal and logging mechanisms because their primary purpose is to have the perception of efficiency. So even though the backend will take time, you have immediately the response that something happened. So that is actually what matters the most to a database person. First, it depends. Second, it depends on the query itself. So if you have just a select from where query, that is not going to update the database itself. So it's just going to be like a read operation on the database. And therefore, it's just applying like a shared lock. Otherwise, if you have explicitly an update, then that is requiring that you're writing something on a table. And then you could also think that you have locks associated to each table, so to speak. So when you're updating one single table, you just have one single lock. But then it would be very dependent on the relational database that you're using. If you're using like Postgres, you might have an implementation. If you're using MySQL, you might have another one, because the only part which is within the standard, and not even all the databases are abiding by the standard, is the query language itself, which is an ISO. But the rest, how you're dealing with the protocol, is just led to the implementation. So you could freely assume that all the read operations are like the select from where, all the updates or the insert or creation of indexes are basically write operations. Does that answer the question? Okay, good. Any other question? So, now let's go in more detail with what concurrency in Java looks like. So, in here, I'm just saying that you have a lot of keywords or package names that are going to be seen, and we're not going to see everything on it today. So this is just providing like a more or less comprehensive list of what we're going to see. We're going to see definitely volatile in this slide, and synchronized, we'll see that on the next set of slides. But so to speak, volatile relates to how I'm caching the data and the results, and synchronized actually works with synchronization. So some of you actually asked whether the coursework is very related to the synchronized. Then if you're using like a YouTube tutorial, it's just because the YouTube person is lazy and they're just providing the straightforward implementation. Like just use synchronized and just use custom Java monitors, but that is not, or because it's actually using very old lectures, but that is actually is not what is used in real life anymore. Because then you have a problem that you will see with monitors. So let's suppose that you want to wait for multiple conditions. Using synchronize is going to be a mess. And we're going to show how actually using reentrant locks is going to be far way better than using synchronized. So it's there in the language for backward compatibility, but it's not very well suitable. So only if you're doing something quite simplistic, like implementing an atomic class, then you could also use synchronized. But anyway, is not encouraged in actual real-world applications. Then we also say wait, notify, and notify all in more detail, because then you have like some kind of differences between how you're using those in monitors and how you're using that in traditional Java monitors. But definitely you could also freely assume that you have basic operations, so to speak, for waiting for a condition or notify that a condition happened. And even though it's implicit within the language, you could also have like a waiting queue, so you have multiple threads waiting for a condition to happen. Then mainly in the older days, you just have thread. I also had another question during the coursework is, why are you not extending thread and you're just implementing basically runnable? Because most of the code that was using thread is, and extending directly that is legacy code, on which thread was actually a class that could be extended, and some method maybe were just key marked as final, but the problem is that thread has all the code also to dialog with a JVM, so with a Java virtual machine, and so if you're extending the wrong method, you could break the traditional behavior of threads entirely. So in order to avoid that, then you're just going to ensure that you're only implementing the run method, then the suggested way is to actually use a runnable and implementing a runnable and implementing the associated run method. So we're going to see throughout the slides only this technique, which is the non-deprecated one, and not to extend the thread, which is deprecated. And then we're going to see concurrency utilities, but we already have a grasp of that in the previous lecture. So for example, you already have like atomic integer. But you also have other concurrent data structures like lists, hash maps, and what have you. Still, if you're just guaranteeing that one variable is atomic, you're not guaranteeing that the entirety of a transaction is atomic. So that's why you need also to be very careful in the coursework. It might happen that you, okay, for your preliminary test that you did, maybe it was happening in an atomic way, but if you're running your code 1,000 times or even more, then I will start to see a problem. So maybe you were very lucky because the operations are quite few and they're happening in the exact order. So we're going to do as much as possible And that's why the test is going to be automated. So we're going to run potentially 1,000, 10,000 tests on your code and see if there is actually one scheduling that is breaking the correctness assumption. And that is actually what I was stating before. So the suggested way is actually to implement run and then to provide the runnable within the thread. And that is also something important. As we will see later on, there is a difference between start and run. And definitely that was actually the issue. So some of the people, so you see here, start, at least in this Java version, was not marked as final. So the problem was that they were, for example, overriding start. And then by doing that, then whenever you were calling start directly, you were not starting the thread, but you were just running the code sequentially. And that might be a problem. So in order to make it explicit that now threads actually implements runnable, where runnable is an interface with run, and you are more than suggested by using run directly. So then you're passing the runnable as in the constructor argument. Then you have another way to initialize a thread, which is also to provide a name, so you don't have, as usually in Java, thread 0, thread 1, thread 2, thread 3. So if you want to help with debugging, you can also provide like an additional name, so you have another constructor that takes also a string as a second argument. And that is actually everything that I already explained in words, but it's just provided in text. So if you need to follow up, whatever I said is actually written in here. And that actually is coming from lazy people still using Java 1.0. Now, while now you have Java 21, so they are back more than 20 versions of Java when you're seeing this kind of code. Yeah, so that is actually just be aware, because that is going to also be crucial when I'm asking tricky questions. Run is actually the way to run the code, but it was just actually not start the thread, it was just run the code. So you could think that the start method is actually the one creating a new thread and then making it run everything that was provided at run. So run, yeah, it has the code, but it's not starting the thread. That's why you need to use start, which is usually the desired thing if you're using a thread class. Otherwise, you are just creating another class and doing the operations. And it also goes back to another question that I was having in the first lecture. So what is actually a lambda? Do I need to use the lambdas, or what are those lambdas about? So, strictly speaking, as I was showing to one of your colleagues on Monday, you could write that because the runnable interface has an annotation which is functional in some extent, that also remarks that the class comes only with one method, and that method should be interpreted as a function. So the run method accepts no argument, as you've seen before, and returns no result. So the question might be, how could I use threads to do a computation and then provide the results? We will see that later on. But then the intuition is like using an anonymous class, so to speak. So that is more like a syntactic sugar or short writing for writing the same kind of stuff that you have on the left. So it's like this part is like creating this new runnable and then overriding the run method and providing the running code. So those are somehow equivalent. And then using the runnable for creating the thread. So, and that's why the reason why I'm showing you that is actually the second line. As I was saying, you could also do the old way, so writing like that, but maybe if you need to write that code in the exam, it's going to take a lot of time. So that is actually a shorthand and is also correct Java syntax. So it's also to make you focus on just the thing that matters the most. And definitely if you're working in a company, then you're also reducing the time for typing, but usually whenever you are implementing something in Java, you're just using like the shortcuts from the IDE, so that should come automatically also. So before I continue, any other question? Yes.
You said in VMware, you said there's like one and two.
Yeah.
Which one should I
Yeah, thanks. I will repeat that. So you see, run, which is actually very ambiguous for the ones providing the specification, but you could think run as being the body method of the thread. So what the thread is doing. But in order to start the thread, you're using the start method. So run is to implement, start is to start the thread. Start will, so if you are seeing, let me show you. Because that is also clear by using the ADI. So if you're looking at the thread, and you're looking at run, run is just trying to see if you have a runnable task, which is actually now the thing that you're passing on the argument, and trying to run that. So you see now is actually deprecated to extend run because they're doing something inside of it. We're just taking the runnable. So now the newer Java versions, that is the way of doing stuff. Otherwise you might break assumptions. So, and everyone says differently is because they kept in the older days of Java, like when the dinosaur crawled the earth. So then if you have start, if you're looking at start, thread start, then you have an invocation of start 0, which is a native method. So maybe you haven't messed up with the Android kernel and you never used like what is called JNI. So JNI is actually the way to run C++ code or platform-related code from Java. That is going to run the architecture-dependent code, which is going to use any kind of operative system specification to start a thread. Or still is going to run a start thread as implemented in the Java virtual machine. So start is actually the thing starting the thread on the Java virtual machine. Does that answer the question? Okay. Any other question? So, then, let's see, so that is also goes with the question that I also had on the first lecture. Why on earth are you doing join? If you're removing the join, the program is going to run nevertheless. So that question is also related to this slide, thread and program termination. A thread terminates when it reaches the end of its run method. Okay, finished completely to do whatever the task I was assigned, or it fails to catch a runtime exception. So the problem is it doesn't have anyone to pass the exception, and so the thread terminates. So the thing that we'll do is to pass the exception to the higher in command, and in this case is actually the thread starting, so the parent thread, the one starting the current thread. So that's why you would see the join method will have also to be catched, and why join throws an exception. Because the other thread could be interrupted or could be aborted, and then by catching the exception of the join at the join level, basically you're getting any kind of issue or interrupt, as we're going to see later on, which is actually going to be not handled by the thread, so you are actually doing this. While, differently, a program terminates when all of its non-daemon threads terminate. So what is the daemon stuff? So you have a way, so usually, let me tell you this. So you could usually when you're writing a program, given that you're not using basically C, there should be a way to create servers that are running in the background without actually having the server apparent. So basically the thing that you want is like having a process which is running under the hood, but is not freezing your console, so to speak. So the thing that is happening is that you're starting your program, you're starting the thread, which is going to be detached from the main thread, and then you're going to make it live its own life while you are quitting. And then the program will not terminate because you have a dabbling thread running along. And that is what a daemon looks like. So the daemon is something that is still running and that will not make the program terminate. So the program will terminate, but you will still have a process running anyhow. While if you have all the threads and you have still one thread being available, running, then the program will not terminate because you will still just see that running. So you will see if you're creating a thread pool and you're not killing the thread pool itself, then all the threads are active and the program will continue to run. So you need to all the time quit all the threads. Or if any of the threads, so thus including the main thread, is calling system exit, that is forcing everyone to quit because you're just returning to the operative system, or system exit 1, 0, what have you. And then we're going to see what are the thread states. But it's going to be better if I show the image, and then if you want to go back and if you want to follow the text, just read the text. That is going to be better. So all the threads will always start in a new state, and the new state is actually the one when the thread is created, basically when you are invoking the constructor and something. Then that is not started yet. So is not within your scheduler set of activity, that is. Then as soon as you're calling start, then is going to be within this state that you see here in blue, which is actually saying, okay, I have all the threads that are started and that are ready to run, but they are not run yet. And which is actually more confusing, they are still called runnable. Either if it is running or not, they are still in a runnable state. Then you'd have a scheduler, which, as I was saying before, you have all the threads, but the scheduler is the one deciding the order of interleave of all the processes. Okay, so the thing that we're doing is basically saying, okay, now you shall run, then you shall stop, and the other one should continue. So the scheduler is actually setting something to run, and then either I have invocation to the yield method, and yield means, okay, I could also wait forever, I'm done. So I could also, for example, I'm waiting for a file to be read or something like that. I do not want to waste everyone's time. So you could also say, okay, I want to yield the computation. So either you are explicitly yielding, which is different for Python yield. So if you're accustomed with Python, yield is just, I have an iterable and I'm returning a value. So that is different from that Python yield. This yield is just to say, okay, I'm yielding to the scheduler to say, okay, now I could also be interrupted because I'm just waiting for something else. This is just to say, I could be waiting. I'm waiting for a wasteful operation, and then I could continue. So very two different kinds of yields. Definitely, then you have something different whether you are blocked or unblocked. But let's start with something very easy. Either the run is returning or is throwing an exception. In any case, from the running state, you could be terminated. So you could see that you shall never return or fail whenever you're waiting for an execution, and the reason why is you're not invoking any kind of instruction. So you are terminated only when you are actually proactively doing something. And then let's go to the blocked waiting or time waiting, and what those are about. So for that, it's actually better to follow the text in here. Blocked is when a thread is waiting for resources such as locks, which is also different from waiting or timed waiting. So, confusingly enough, you have different waits on something could be waiting. So locks is actually something that we're going to see tomorrow. So I'm just ensuring mutual access to something, and then it's when something is blocked. Otherwise, I have a difference between waiting and timed waiting, which are still referring to invoking methods such as wait or join. And I know the confusing part is that you're not seeing everything in one shot, but if I will telling you everything immediately, it will be overwhelming you. So for the moment, the thing that makes sense is just the join. Even when you're joining a thread that you previously created, then you're waiting for something. So you're waiting for the thread itself to be completed. Or you could also wait for a condition, and this wait on the object will be clear once we're going to see monitors, so tomorrow. But you also have other alternatives, which are having a timed wait or definitely you could also specify that you want to wait for a given time, and then you are rerunning the computation and you're going back. And that is going to be similar whenever you have sleep. You can also specify for how much time you are waiting for something, and then after this time, then you're going to regain control. And all the time, while those are actually requiring you to catch an exception, because all the time that you're waiting for a condition, then you could be interrupted. So with a join is because the thread that you are waiting for might be forcibly interrupted in the terms of killed, or is not catching an exception, and then you want to know what went wrong with the thread, or another thread send an interrupt and partially partially stopped momentarily, temporarily the execution of the thread, that then will be continuous, or anything of the like. In here, I know that I'm waiting, but with some time, so I'm providing a timeout, after which I will stop waiting for something. And given that they are actually doing something similar, they're going to be always associated to the same state, which is either blocked or waiting or timed waiting. And after waiting, Java, how it is implemented, is just not making it run necessarily again. It's just making that in a waiting state. And after that, after the wait is done, or after the thread is unblocked, then it's going to be like a scheduling state. Because then I need to double check if I'll give a priority, for example, to another thread to run. That is actually the main reason. So that is just from a theoretical standpoint, but as we're going to see then, we're going also to see more practical examples. Do you have any questions regarding this slide? And before doing a break? So just something very easy, because then we need to discuss volatile. I need your attention for that. So these are just all the methods that you have in there. So you have yield, you have sleep, and you know that all the things that are waiting for something are also throwing an interrupted exception. And you could also check for the state of the object, so whether something was interrupted or is interrupted, which are somehow similar. You could also get whether that is alive, or you could also get the name of a current thread, because you could also use what is the purpose of that. Basically, you could use the same class for generating different threads, and you want to get like the distinctive name. The other way is actually setting, the other thing that you could also do is actually getting the priority of the object. We're not going to see that on purpose, because the thing that I was told by other students, okay, but if you have like, as we'll see later on, from following days, like tomorrow. But if you have some problem called starvation, where one process is actually not making it to finalize the computation because other processes are actually faster and are always catching up, and the other process is always lagging behind, then we'll just increase the priority, and then, well, that will be easier. No, that will just escalate the problem. So if you're just increasing the priority, then you're just solving the problem maybe once, but not necessarily you are solving that definitely. So the only way to avoid starvation, as we're going to say over time, is going to be create a better program rather than increase the priority. The priority is actually used for another purpose, which is what should be constantly be updated, so it should be run with a priority, and what should be lagging behind. So for example, you could think about the thread associated to updating a graphical user interface should have a greater priority than the thing waiting for an update from a relational database or something, because then you want to be as responsive as possible, but maybe the data that you are computing might be slow to do. So it's just to assign priority and execution, but not actually to solve concurrency issues. So then if you have no questions, I will do a break, and then we will start again within 10 minutes. So, then the other question could be, if you have, then the other question could be, if you have basically a class, and then you want to use like a thread and a body associated to that, how could I do? Then in here in the slides I'm instructing as follows. If using an anonymous class, providing like a thread implementation, use an anonymous constructor. So that might puzzle students. What is an anonymous class? What is an anonymous constructor? Basically, I'm providing now a use case in here. You have an abstract class, but in here actually have a class, because then I decided to do something like this. And within this class, so it's not abstract anymore. So I have a public class on which I have like a runnable method, and I'm using a constructor. But basically, I want to, let's say that I want to change the way I'm implementing this method. And let's say that this is actually a public abstract thought. Something like this. Then I have a class which is abstract, and then I want to implement on the fly just the print message stuff. So let's suppose that then you have all the logic, but then the way the threads will differ will be just in the way they printed the message. So the first one entails that one way to start to create a new thread and to pass data, because then the thing that you want is to print the message, is to do the following. You are creating a new variable, and then you're saying new, what is the name of the class, for runnable, and then in here, the thing that you want to do is to provide the message, and then you might provide, for example, the external message, but you see that is not enough, because then you need also to add then you need also to implement a method. So basically you need to do this. Okay, public static abstract class, yes. So the thing that I'm doing in here is, how could I definitely pass some arguments? For example, I create a class which is abstract, as you see in here. So it was the same idea for the runnable, basically. So I know that if I'm passing some data to the program arguments, then that is going, for example, to be the message that is going to be printed. Then if I do new thread d start or something like that, and I'm running this, you'd see that I print hello world. So in some way I'm creating a new runnable, and then this in the constructor I already passing all the data that is actually required to be run, and then I'm implementing just some methods that are required. So that is one way to pass the data. Another way that is actually said in here is accessing an external final field or variable. So what does that mean? let me show you that in practice, then you want to do the same stuff, but now you want to access the external variable, so you could do system out println, and then you're using the external message. In this way, that is possible because I'm not changing this variable all the time, and that is if I'm writing final. So the compiler knows, so given that strings usually in Java are like non-editable objects, so if you are changing the variable, you are forced to create something new, or still from the code, it knows that you're not going to change the variable, so you could also access that within the thread. So the other thing that you could also do is to take directly the data from the outside and doing that as such. And then you could also be something more complicated, which is using a static time constructor. Why on earth that might be required? For example, I do not want to exactly print the external message, but I'm creating a new variable, and for the external message, I want to trim it, and in here I'm forced to say that that is a string, and then I'm just doing, not exactly using the external variable, but something else after it. So you could also do split into declaration and initialization, and that is actually what I meant. So you could also have the declaration of a variable, and then you have an implicit constructor in there, which is going to be run when the new runnable is going to be created. So let's suppose that in the string you have some empty spaces like such, but you do not want to print that string, but just the string trimmed of the empty spaces. So you see the thing that is going to be printed is still hello world without the empty spaces, just to show that that change is actually effective. If I'm removing the trim, you see now the string is actually changed. So if I want to take the data externally, but also to changing the bit, I could also do it this way. I create like a temporary constructor, so I'm implementing something, so I'm not allowed to create a new constructor using lambda syntax, but I want to take some variable and to do some operations, then you're still allowed to do that in this way. So all these three methodologies that are listed in this slide is the thing that I demonstrated now. So by the end of this day, I'm going to update also the code base, so you have a better reference of what I was talking about and this code base, so you're not required to type everything. So that is actually just what it meant. I'm just showcasing that to you. Then it might be without reason for you, but now we need also to discuss the Java memory model. Why? Because a lot of problems that you're going to use at the very easy, so the easiest problems that you're going to see are due to the way Java organizes the memory. And as you will see, you have, as I was discussing from the very first lecture, the processor is not accessing directly the data from the CPU, and it has some registries where you're actually performing the operations. But we need to add to the realism another layer of complexity. Unfortunately, you do not even have that, you also have a cache between the processor and the primary memory. So you're not necessarily having the latest information that you have in primary memory, because in order to fastly access the information, you're saying, okay, I'm confident that the data somehow is updated, and then I'm keeping some data in the cache, and then automatically the program will know whether I need to refresh the value or not. So everything is actually implicit of what I need to do from the code base itself. And the problem would be still, if you are, given that you're using a high-level language, you are not allowed to see what is actually happening under the hood, and you see the abstraction that the programming language wants you to see. So given that you are still seeing the value from the cache, and not directly the thing in primary memory, there you might not see necessarily the most updated value. And so there are some set of memory rules that we're not going to investigate into detail, because that will also require that you have a module on operative systems. But in here, I'm just providing you the brief amount of knowledge required to understand volatile, as we're going to see today. And we're going to see only one rule regarding the way the memory is updated, which is the one regarding volatile. So this in the picture on the right is actually the thing that I'm talking about. So you have a thread running on one single CPU, and you have a cache which is mediating the access to the memory. So no matter how one thread is updating the memory, given that everything is bounded by the clock tick, is not necessarily given that the value that the other process is reading is the most updated value, but it might be the value that you have in the cache. So the problem is, how do I ensure that I'm avoiding basically taking the value from the cache, is to explicitly declare one variable as volatile. So that is actually forcing the language to avoid any kind of caching mechanism for that variable, while requiring to always access the value under the assumption that it's going to be very fastly updated. And that is strictly required whenever you have variables that are shared across threads. So you can also think that if you have one thread running and this data is not shared, that would also rely on the cache. And so you don't have problem of mutual visibility and update for the primary memory, because even if you're just updating the cache and this is actually your internal variable, that is still going to be efficient enough, and that you should do. On the other hand, if you have requirements for communicating across threads, then you need to ensure that the value that you're getting is actually always the most updated one, and therefore you want to instruct Java to directly access the memory. So then when the program will be compiled in Java bytecode, then instead of, so it's going to force the Java bytecode to access all the time the value from primary memory and not to use the cache at all. Yeah. So, and that is why that is ensuring that you're accessing the lastly written value. And the other thing that is doing as a consequence is also ensuring that all the operations are going to be atomic if they are fitting, as we were discussing before, the word size. As we were discussing on Monday, that is relevant because you could think that the CPU will do all the instructions in one tick, and that tick could do operations on the size of the word. So if you have like a 64 architecture, you could also do operations either on floats or on doubles or on longs, which are either 32 or 64 size. But if you have a 32 architecture and you're trying to update a long, then you'd require 2 ticks of the clock so to fully update the variable. But as we were discussing before, that does not prevent that you could also have increment operations with a plus plus, and so you're reading the value, then you're incrementing and are setting that, so that is not enforcing that an increment operation is atomic. Just simple read and write operations are ensured to be atomic and shared across the elements. Because you also have another problem, which is called, even more confusingly enough, reordering problem. So it might seem that you have the program being shuffled around, but that is actually not even what is happening under the hood. So what does that mean? A rewriting problem is happening when you have 2 threads, and given that you have 2 variables which are not declared volatile, okay, you have the perception that the operations within the A and B methods being used by this kind of threads, which are runnable, are if the operations are interleaved. So I'm not doing x equals 3 first and then y equals 4, or I'm not getting the value from y and then I'm not incrementing z and I'm not returning z, but I'm shuffling a bit the order of operations. So this problem, when the variables are not declared volatile, is called reordering problem, because the thing that you're perceiving is as if the program was rewritten. The problem is not that the bytecode is shuffled. The thing that is happening is that the caching mechanism is in play, and therefore it appears that given that the other thread is not accessing the latest value, that is like, and given that the cache arbitrarily decides in the way to update the primary memory due to these internal specifications, so maybe one variable is frequently accessed, and so I want to update this variable first, but then this variable which is frequently accessed was accessed last, and beforehand if the program accessed a variable which is less frequent, and there the order of priority is actually inverse if compared to the order of instruction of the program, and so it appears like if the program was reordered. So you'd see like the variables were updated in the exact opposite order, but that could be avoided by declaring both variables as volatile, and by doing that, the thing that you're ensuring is you to have always access to the variable x or y in the exact order, and given that those are both volatile, you're always accessing the latest updated value, and thus you are avoiding the reordering problem. Now we'll stop. Is that clear? Do you have questions regarding volatile and the reordering problem? Yes?
Is this similar to the serializability thing? All the swaps,
No. Let me clarify on that. So thanks for the question. So the serializability refers to something different. So in there, you're always assuming that the program will run for each thread from the beginning to the end. The only thing that you are perceiving is that the final state of the program, which is the values of the global variables, are not as, are not as the program was run in a serial way by just running all the threads compactly all the time. Nevertheless, this kind of problem would also occur no matter how you are interleaving the execution of the two threads. So it's not related to the interleave of execution of the two threads, rather than to the caching mechanism. So you are subverting, so the perception of the final state is as if one single thread, or both threads, as far as I'm concerned, are the order of their instructions swapped. So it's like doing y equals 4 and then x equals 3, which is different from having x equals 3 and then the operation from the other thread and then y equals 4. So the serializability or the serial are concerned about the final state of the program and whether, even though I'm interleaving without swapping the operations, then the final state corresponds to the final value of the variables at the end of execution, corresponds to different threads running just each of one completely by itself. This is actually a problem that you will never get with non-serializability, because serializability is not assuming any kind of caching mechanism under the hood, because it's a theoretical definition. This is actually more concrete, and it is also assuming that you have a cache underneath that given the different times where the variables might be updated, and given that the variables are shared across the threads, so the perception is as if the operations are reordered, but not in terms of interleaving, in terms of actually swapping the operations, because I'm seeing the other thread is seeing the variable y updated first rather than seeing the update of 3. Because maybe another thread is frequently accessing the same memory location for y, and so it prioritizes to update y rather than to update x first. So you have another caching mechanism which is actually called RU, which is actually prioritizing the most frequent first, basically. So if you have like an RLU running, then you're going to prioritize the order to the updates and to keep in cache basically the values that are already available. So, and that is completely independent from the order that I'm executing something. It's just not promptly updating something, and then the other threads perceives as if y was updated first. And then, that is what's called reordering, but it's not related to the ordering of the program, it's the perception as if the instructions were swapped, but the problem is not the instructions are actually swapped in the bytecode, it's just that the cache is updated in different times, differently from the time the variables were updated. I don't know whether that answers the questions or not. Okay. Any other question? And that is actually still restating everything that I stated before. So the volatile is like disabling the cache, so is instructing the bytecode or what have you to always get the freshest value from directly from the primary memory. So it's like disabling the cache for that variable. So whenever I'm doing a read or a write operation, I'm directly operating with the primary memory. It might be slower, but hey, I'm ensuring atomicity or avoiding the reordering problem. And that is everything that I was restating. So I'm just providing like an expanded explanation if you might want to have more information about something, which is I'm expanding on this 2 brief sentences in here. So that is what the current slide that I'm showing now is about. I'm just saying that you have a long or a double that in Java are actually 64 size. And so those are not going to be atomically updated if your architecture is 32-bit. So, and then in here is just restating what reordering is. So unless I'm specifying volatile, then I'm not ensuring to see the updates in the same way that I'm doing. And that is actually the other thing that I also mentioned before. Volatile is not strong enough to also consider increments as such as atomic, because still from the CPU perspective, then you're doing 2 instructions in a row. You're doing a read, actually 3. You're doing a read, incrementing temporary value, and then setting the value back. So that is not going to be guaranteed to be atomic because the CPU clock is going to run 1 operation at a time. So it's not going to be atomic at all. And in order to make so I know that also one of you that also did the exam 4 actually used atomic integers and then the locks, which is actually like using braces and belts. So I'm using atomic locks for safeguarding a variable, and then within the lock I'm also using atomic integer. But that is actually to the lesser avail because you're still safeguarding the access to the variable, and then you're therefore even again safeguarding. So you're adding somehow of an overhead, computationally speaking. On the other hand, if you are within the lock, then you could also avoid using an atomic integer to what I'm concerned. And that is actually the exercise, showing you what is the effect of the atomic class and how this will ensure basically the atomicity of a plus plus operator. So I will leave you to that as an exercise, but you have the code base in here. so you don't need to retype everything, which I think is preposterous and useless somehow. So if you're going to concurrent Java, then you have atomic atomic shared counter, and you have the same class. So for you, if you want to do that as an exercise, it's very easy. Just remove the increment and get, replace that with a plus plus, and then replacing atomic integer with an int. Then what will that happen? And then it's just for you to get. So that is just to show that basically the int increment is not atomic, and you need, in order to ensure that more than one instruction is atomic, then you need to safeguard the entire execution itself. Similarly to what increment and get is doing. And then that is actually the extended code basis. And then in there, basically, I'm showing what should be done, which is just incrementing AI directly rather than, it could also be int, not necessarily integer, but that will do. If you're doing that, then you'd see the difference between the previous one and the atomic integer. So then the other question is, I have two threads that are running. How could I ensure that they're actually accessing the same variable? So one simplistic thing could be instantiating multiple threads from the same class, as allegedly we're doing here, you see. But it's not even the case, so that is not the case. Because in here, definitely you're creating multiple instances of R. Yeah, no, sorry, that is the case. Why? Because this variable is perceived as global because actually it is shared across all the threads, because it is actually a field of a class itself, my class, and it's not a field of R. If integer AI would have been a field of class R, then all the changes to AI would have been local to the class R. By declaring AI as a field of my class, which is accessed by all the threads, then that is actually a way to ensure that it's actually going to be global. Another way, as also stated in the slides, to make AI global, but still putting that inside the class R, is, for example, to declare that variable as static. And by making that static, you'd know that that is actually a variable which is actually associated to the class directly and not to a specific instance of the object associated to the class. So those are two possible ways. The static, the second one I provided. And the first one is actually, given that in Java is going to be different than, for example, C or C++, where unless you are explicitly stating that, then all the objects are passed by copy, you need to basically use a pointer or an @ to say that that is actually a reference. So you're passing by pointer or passing by reference explicitly. And otherwise, if you're not doing that, you're passing by copy. In Java, you're always passing by reference, which means whatever the thing that you're providing to the program argument in the method is going to be the reference to an object, so you could directly change that, which is not a very good safety guarantee, but that is actually how they design the language. And then the thing is, if you're passing something to be shared into a constructor, like for example the atomic integer, and that is actually going to be in the main, and then whenever you're creating R, you're passing the same atomic integer to the constructor, then you're not passing a copy, you're actually passing the same object. And so even though AI will be like a private field of a class, still the thing that you're passing is going to be the same object across all the threads, and that is also acting as a global variable. So then the thing is, how could I achieve that? Then another minor exercise is to rewrite that in these two ways. But that will be just a matter of coding if you're not already accustomed with that. So the other thing is, now we're going to see usually yield, sleep, and join. mainly sleep for what I'm concerned, as well as interrupt, priority, and threaded groups. But yeah, just the interrupts as far as I'm concerned. And then there is actually a reason why those are deprecated. So you might see that in old material that you find online, like how to stop a thread, destroy a thread, suspend or resume, but those are deprecated because the implementation was somehow cranky or clunky, and then as a consequence, the thing that you had is that you messed up with internal Java state. And therefore, as a consequence, you have like an unstable overall execution. So, in order to achieve safe programming, it's actually better that you're using other kind of methodologies for stopping threads. And that is actually mainly due, as far as I'm concerned, to a problem with implementation in C or C++ of P threads, where also now stopping explicitly a thread using the standard API is deprecated or not even allowed. While if you're having a process like in the operating system, I'm not considering Windows, on which if you're using like the task manager and you're trying to kill a program, it will even not kill itself. While if you're using Linux and you're sending like a seek termination instruction like 9 or 15, then it's going to kill the process itself. So that is going to be safe somehow if you're killing an entire process for the main reason, that is actually the reason why doing those is not safe also, for the internal state of the program, because if you're doing a stop operation and that also relates to one single thread, that is also related to atomicity, maybe it's just doing partial computation and is not committing or updating everything, so the other remaining threads might have like an incomplete state. While if you're killing an entire process, then you're killing everything else, and the other process will not be affected to some extent by the internal state of the process itself. So to avoid any kind of problems or issues, either at the JVM level or at the consistency of the variables, we'll make just these methods deprecated. And I think that, yeah, the last thing that is left, but then we also have 15 minutes, is actually discussing interrupting threads, which is still allowed in here. And then I'm going to see the example in the slides running. The other thing is similar to some of you accustomed with C might have experienced before, is also possible to send signals or interrupts to threads so they know that something happened. Let's see. Actually, signals are the way in C++ threads, exceptions are implemented. So basically, you're sending a message. And then you have a signal handler at some level that is going to catch the signal because it's actually relying on low-level primitives. So it's actually possible to send a message which is not a text, but is like poking someone. So that is actually what a signal is. It's like in the old Facebook when you're sending a poke. So you receive the poke and then what you're doing, you just receive an interrupt. So there you're just going to be suddenly interrupted or waiting, and then you are resuming your computation. Essentially, so in here, if the other thread is actually waiting for it, then I'm going to get the interrupted exception because I know that the thread I was waiting for was interrupted. And then, as a consequence, the other one that is so that is actually the reason why those are basically as such. So if I have no thread to wait, if I'm sleeping for a given amount, then the sleep will give the opportunity of receiving the interrupt, and join will actually be the way to know that, for example, another thread was interrupted. And that is actually related to the coursework, but it's actually not mandatory. If the thread is waiting for a message, we can assume that a specific message might stop the thread. So how do I avoid that? Then the question is actually open to you. The idea would be, even in the coursework, you just have to have a look at the code base. Whenever there is a part where I'm waiting for a message or an event to happen, and let's see how that might be implemented. So even in the coursework, I'm not prioritizing one specific implementation as soon as all the tests pass. So it's completely up to you how you're implementing the method. The important part is that the tests are passing. And then you have to provide a better explanation of this code, but I think that it's going to be better if we're seeing the code live and running. So, this is actually the same example from the slides itself, on which you are having a main thread, which is starting the program, and then you have basically the thread that you are creating, which is waiting for a given time, and while waiting with this sleep, so given that it's not waiting for anything else, is actually waiting for interrupts to occur. So I want to send a message, and this message is just, I'm sending an exception basically, which is caught. So one thread will just wait for some amount of time, so it's waiting at least for 1 second, that is 200 milliseconds times 5. And the other one, so the main thread will start this waiting thread, waiting for interrupts, and is going to also wait for 200 times, but less than that, like 3, and then at some time is going to interrupt the other thread. So you'd see something weird happening, which is also going to be scheduler dependent. You see, if now you have all the 3 times I had an interrupt, also in this time you have all the 3 times. But that might be very much scheduler dependent. So in here I'm actually ensuring that all the time I'm catching the exception. But what if the other thread is actually very fast? So in this example, you have no exception, no interrupt being caught at all. Why? So that is actually what I mean. I'm providing you the code so you could play with that in order to answer your own questions that you'd have related to the theory. So the thing that happens is that the thread will catch this interrupt only if the thread is waiting for a condition or is waiting for something. Only on that occasion then the thread will be receptive to catch the message or the interrupt that is actually receiving. So in this example, I provided a very short lifespan to the thread, like 1 millisecond, and the other method in here was waiting for 200 milliseconds. So all the time it was waiting, the other one was very likely to be already finished, and therefore, as a consequence, the other thread didn't ever have the chance of getting the interrupt, and so you had no message being received at all. That is also to make you reason about the scheduling order. Well, on the other hand, if I'm doing the similar stuff, but I'm doing the interrupt, and then I'm shoving the wait afterwards, it might happen that at least I'm catching that one time as it's happening. Why? Because very fortunately I'm sleeping for 1 millisecond or other times, and then I was very likely to get, how do you say, at least one interruption from that. And that was actually happening at the first time, directly. So if I'm changing also the sleeping time into 3, and I'm providing more iterations, then you see the other thread is actually trying to send 3 interrupts, but the thread waiting, even though it's running 50 times, is only catching 2 interrupts overall. So you have like a lost information So basically you're sending a signal to another thread which is not waiting as required, and so if your program wanted to wait for all the 50 times or all the 3 times, then there is actually something wrong with your program. So beyond the simplistic fact of waiting for a condition, and from the fact that changing the timestamp or changing the way the processes are scheduled forcibly by changing the waiting times or the number of iterations, that should also remind you something relevant from once we were going to start seeing the logs, which is if a thread is too fast and is not waiting for a condition, then you might signal something, but the signal is not received because the other thread was not receptive for receiving the synchronization information. So you always need to ensure that the other thread is receptive to that. And the main reason is that because these mechanisms are not using like memory for remembering, okay, I was sending a message or sending a notification, then do I have something, then I'm reading the message. So it's not going to act like as a message passing. I'm just sending an interrupt, and if I was not too fast to catch it, then I have no information whatsoever. So that's why, for that purpose, you're more accustomed to use emails rather than to handling operating system interrupts. So that's why I think that showing you semaphores at the very beginning will not provide the right understanding on how the machine works, because adding semaphores will be just adding a remembering or a counting mechanism, so to remember that I was sending a message or I was sending a signal to another process. So first I want to hit on the fact that you might lose information if you're using like efficient primitives, and then if you want to do more, then we're going to see semaphores, but otherwise you have the wrong perception that you always have the information, and no matter how you're sending the message. So that's it for today, but before I'm dismissing class, do you have questions regarding interrupts, regarding anything that was taught today or any other earlier day? No questions? Then, if not, then we're going to see each other during the practical session.